what we're going to do is we're going to do a little twisty thing. The same trick with the twisty family, we're going to apply it to just a general string length. See what happens. Kind of follow how things change. And so, and this is going to be, this trick is actually going to give us an interesting result. So if we twist this guy, we get this. We can actually use information about the limit representation of the original string length to get information about this new string length. I'm short on time. Yeah, so I'll blast through it. So you can use the limit representation of the original guy to figure out the limit representation of the twisted guy. You can also apply this gain representation here to kind of figure out what the limit representation, this gain representation of the new guy is in terms of the old guy. So what I did is I picked this guy, and then I smoothed out switch crossings that simplifies to that. And we actually do the apply this gain representation. And yeah, that can be smoothed out as well. Because notice here, I can just pull this one up, pull that one down. It simplifies a lot. So you get that. So you get the scanner. So what I'm going to get is a nice, simple expression in terms of itself. When I get not that simple actually, because remember I have to apply psi first and epsilon, so it's not so simple. But I get something. And what I get is, after I do some work and identifying the corresponding, because remember I assume that it's true for all string lengths of 2 strands. So when I do this, it should still be true. And I get different entries for the things, well, seemingly different entries, but if I make them all equal to each other and solve, I get an interesting result. That the Alexander polynomial, which is a very important thing in knot theory, the Alexander polynomial of the closure of a length. So take a length and then take these ends and close it. You get a knot. It's going to be like a circle but really tangled up. The Alexander polynomial of the closure of a string length is equal to exactly that times the 2-1 entry of the side part of the string length. And I have no idea if this is known or easily derivable from known results, but it is something. And that was, people would like this, it seems. And so that was a consequence of assuming it's true just for n equals 2. I don't care if it's true for n equals 3 or 27. If it's true for n equals 2, we can get this for free. And I mean, it makes you imagine what would happen if we do other operations and we get other interesting identities with Alexander polynomial. Maybe. I didn't get a chance to do that. But many examples for this thing have been checked. Like I tried, my advisor said, check it for a couple of knots, and I did, and it checked out. So it could, it's another way of providing evidence that conjecture could be true, at least for n equals 2. And so the big question is, are they equal? And so that's pretty much where I'd like to end the talk. And references, any questions? I don't think we have time for questions. Any questions? I left it there so you can point to mouse.
During the recent program, did they show you what applications this is? Because this looks like this is very easily applicable.
To within mathematics, you're saying?
I mean outside.
Outside mathematics? Well, I actually had to, when I made the prototype of this presentation, because I had to make like a 15-minute presentation there, I had to come up with such things because there was mostly physics people there and things like I'm not math. I was the only math person there, and a computer science person. Yeah, so I had to come up with some applications, so I made stuff up. So you have applications not there, obviously, and you have you can knot DNA, and so that's actually kind of interesting because they use the theory of tangles to understand how enzymes transform DNA. So tangle theory is actually useful for DNA, it turns out. So maybe this is useful for DNA as well. Just because it's there, that's really why we did it. There's not, you don't, yeah. That's really that's the applications. Yeah. So maybe there's application. I expect in 300 years, okay. No, up or down. Yeah. Any other questions? Like examples or something?
When was this done? So how recent is
this was the summer. Lind's representation.
Yeah.
Lind's representation was done in like somewhere between 2003 and 2010. Lind's representation is pretty new. My advisor did his thesis, which he did this whole representation of Tangles within 2000, 2010 also. I don't know when that is. So it was, I think it's his mentor, I'm not even sure, I think his mentor, he noticed this and he started thinking about it, but they never got the time, I guess, to really look into it. So before I got into it, there was only one example, but they agreed. Well, technically, it agrees for all braids, but there was only one non-trivial string length where it agreed up to that point, so I found one.
For physics, string theory will does this have any consequences to
Yes.
string theory? Yes.
I don't know.
Or this has anything to do with
Maybe. I mean,
the strings in
really what's
string
happening
theory in physics, are they the same as the ones that you presented?
from what I understand, the strings in string theory are just closed. Well, you have open ones, but they're usually only made of one strand, so you can have closed strings. I don't know if they're allowed to mount themselves, but they just vibrate in different ways to generate the different particles physics. But I don't think that it's really, because the one strands are very simple in this case, and we don't really take into account dynamics, like what happens if you started shaking them, or things like that. An interesting thing Lynn did, though, is I guess he did find an application for physics somewhat. Is if you imagine a strictly positive string length where all the crossings are positive, then notice all my probabilities can actually be interpreted as probabilities. I have 1 minus t's and t's, right? So I can just say t is equal to 1/2. So you have a probability of 1/2 following, probability of 1/2 continuing. So I can actually give it a real probabilistic interpretation. And so imagine laying out an electrical circuit, or some section of an electrical circuit, where the strands are wires, and current can leak out from the top ones to the bottom ones. And so then you can ask the question, what is the final current at the end based on how things are leaking? So that could be, I'm not exactly sure how useful that is, or he just kind of added that there to make the physics better. But yeah, so you could have that. But other applications in physics I'm not too sure about. I think maybe the DNA knots is probably, I mean, I'm sure, I know in physics they use knot theory and stuff. I don't know how.
Well, like materials engineering.
Materials engineering?
Yeah, like designing certain fabrics, like Kevlar or whatever. They have certain braids.
There you go. So perhaps.
Could you start with more simplistic representations, like in graph theory, like bipartite graphs, for instance? So,
What do you mean by most simplistic representations?
like instead of starting with knots, you start with graphs, and then you work your way
Instead of knots,
or
graphs.
links, string
Instead of
links.
graphs with knots. The thing is, graphs don't have a natural algebraic structure. I mean, what do you mean by multiplication of graphs?
Oh yeah.
Yeah, first you have to define that, and then you can ask questions. So you could, if you wanted to, define a multiplication of graphs, or some subset of graphs that are amenable to multiplication, and then talk about representations there. But you first have to define that, and then you have to kind of convince everybody else that it's an interesting definition. With braids, there's a natural multiplication. I mean, braids are very useful in mathematics. So, and the multiplication.
Oh yeah, I think graph theory is applicable. You can show how many of the sinks and sources can be linked before you have to cross over one.
I tried to be honest. First week I was there, I tried to do graph theory.
That's what you use the four-color theorem for. The four-color theorem, it basically says that you can only have so many edges touching before you have to cross another edge. If you cross an edge, then you have to redefine it in the planar space.
There could be lots of things.
And if you redefine it in the planar space, and you show that one has to go under or over another string.
It's really not so easy, I feel, because things can be deformed. You can hide things that you didn't think were there. Like things, it could be in a shape that when you look at it, you don't think it would look like when you the simplest diagram. You can make it very complex. So it's you can introduce crossings where there wasn't before just by twisting things and adding. So I wouldn't know where to put the graph. I tried for the first week to do graph theory stuff because I thought, hey, there's graph theory. Anytime there's a crossing, I can make that a vertex, and anytime, I do that. But it's really hard. It's not very easy. So I couldn't really figure anything out that way. So I just started doing it in geometrical. That's it then.
You will have Doug Dr. Lawrence, the graduate student in physics, to talk to us about fictitious courses.